We started off with a continuous signal over here, which we sampled. We introduced this mathematically convenient object, a pulse train object, where we encoded the values of the sampled signal at the sampling intervals as the magnitude of these Dirac delta impulses. Now, I've taken care here to draw these without a height, because theoretically these Dirac deltas, if you were to be able to plot them, remember they would be infinitely high, right? So these Dirac deltas are infinitely high and infinitely narrow, but then paradoxically they have a surface area which varies based on their coefficient. And that's basically what we're getting when we multiply this delta over here, which is the shifted delta. So every one of these deltas, a delta at 0 would simply be delta at t. A delta shifted up by one sampling interval is delta t minus delta t minus 2 delta t minus 3 delta t, and so on. Okay? And so this is an infinite series of these Dirac deltas, and when we Laplace transform that, and why are we Laplace transforming? Why? Because we are trying to go through the same motions that we've been going through. And up to now, if I hadn't told you about this trick, you would have been perhaps a bit confused about how you would go about calculating the Laplace transform of this new discrete object. I've taken great pains to say that this thing doesn't actually exist between the times. It's not a continuous thing. How would you do this continuous Laplace integral? And so we're doing a trick here, which I want you to understand, is that all of this working over here is kind of just the mathematical sleight of hand that we use to encode these sampled signals within the Laplace domain. And when we do that, because we're shifting, because of all these deltas being shifted, we end up with a lot of these exponential terms, right? Because moving a time signal up by a certain amount corresponds to multiplying in the Laplace domain by this exponential. And we came across that many times when we were thinking about dead time. And we also, if you were preparing for semester test 2, and you were looking at a couple of questions where I asked you to calculate the Laplace transform of some random arbitrary input signal, you would have seen these exponentials again and again and again, right? Because it's the step times the exponential to move it up that amount. Now we're just not doing steps and ramps, we're now just doing deltas. So it's the same concept and should look pretty familiar. And kind of one version of telling the story is to say, well, you know, my hand gets tired and I don't want to write so much, so I introduce this thing called Z, which is just this straight up substitution. It's just a notational convenience. I could have just written S all the time, but instead I'm writing Z. And in this version, when we look at something like this, the mechanics of doing that calculation looks something like this. Take the original F, right? Evaluate the original F at the sampling points, and then multiply each one of those coefficients by an appropriately delayed exponential, which by the time we've done the substitution looks like an appropriately powered Z. Okay? And while we're looking at these formulae, I want you to also kind of think about another interpretation of Z, which is that Z effectively is a shift operator. In other words, if we were thinking of Z being a transfer function, right? If Z weren't like part of the signal, but rather something that operated on the signal, we would say that like Z to the minus 1 would have the property of delaying the input signal by one time step. Is that clear to everybody? And that actually is the answer to the slightly more interesting question of how do I get generalized versions of input signals if I have such a small list of signals in my table? And the answer is, again, that we can express most signals as combinations of these smaller signals. Just like we could write in the Laplace domain, we could take a signal like this and recognize that that is a ramp and another ramp and another ramp right? That those three, that triangular shape could be expressed as the sum of three shifted ramps, right? We could also say that most discrete inputs can be seen as the sum of shifted inputs in the same way. Now, because of the sampling, there's a little problem about uniqueness, okay? Because remember, by the time we actually look at this signal, we're only looking at particular points. And so already we can see that there's not necessarily going to be a 100% unique description of that signal in terms of the building blocks. Does that make sense to everybody? Because I could express a signal like this, which, let's for argument's sake say this signal is now a shifted version of the step. I could express that as what I know the unit step function is, multiplied by, and that version there would be multiplied by z to the minus 2. Is that making sense to everybody? Why? Because I am shifting the original step, which started at time 0, up by 2 sampling steps, so that it now starts at time 2, or at time step 2. Okay? So that's one way of thinking about this, and this is a valid version of events. But if I had something like a ramp transfer function, okay, so notice that I've got here, I have a sampled ramp. Now the idea is, and I'm not going to write down the math, but I just want to draw the picture so that you have an idea of what I'm talking about. If I have a sampled ramp like that, and I sample it only up to this point, it has all exactly the same output values as a step that starts at that same time, or that starts one time later. There's no way for me to distinguish between those two if I just look at the values of the coefficients. Is that clear? And so it's not unique. I could have said, you know what, I'm going to encode that as a ramp. I could have done that. And I would have gotten exactly the same coefficients out. But the building blocks would be different. Instead of the step transfer function that I have here, I would have a ramp transfer function starting one time step earlier, another ramp transfer function going down to cancel that one out. And so you can imagine that this means that the math must work out the way that if I actually work out the final result, I'll get exactly the same coefficients out. That's true. Unfortunately, it is not true that these series expressions will be exactly the same. So there is a little bit of a problem of uniqueness. Now, I don't expect you to worry about that too much, but I just want you to understand that by the time we start introducing discrete signals, the fact that we have stuff happening between the signals destroys our concept of a unique transform. So why am I saying this? Because I want to go now to the function system, or let's maybe start with the inverse, and what we would mean by inverting the Z transform. So when we were working with the Laplace transform, this question had a very clear answer, right? Remember, if we looked in the table, this is the data sheet, right? If we looked in the table, in the data sheet table, we had f of t and we had f of s, right? And f of t could look like this, and let's say f of t could look like this, and f of s could look like this. And if I gave you the one, you would always know how to get the other, which is to go backwards in the table. Right? Now, if you're the kind of person who likes making drawings on the handout, I would like you to draw a line that separates the continuous domain from the discrete domain on your table. Because this this table only goes one way. Right? So you could very easily say, okay, if I Laplace this, I get that. If I inverse Laplace this, I get that, when we were doing continuous stuff. Now, you would like to say, I understand the symmetry. The urge to symmetry is very strong, but I want you to understand that this is not true. You would want to say that that f of z is what you get when you z transform f of t. And this is wrong. Okay, this is not what is in that table. Okay, what is in that table is the z transform of f star of t. Okay, so that's the first thing, is if you wanted to do something, you would have to introduce a sampler in that operation as well. In other words, this is not the z transform acting on f of t, right? This is a thing that I do to a sampled version of f of t. And why this is important is because there is no inverse. There is no way to look at a function of z and recover the function of t that was sampled in order to arrive at that point. This is a place where people are incredibly confused, and I'm trying mightily to kind of make sure that we have the least confusing version of this possible, right? So the first question is, if it isn't possible, like, why isn't it possible? Why can I not notice with my eyes that this thing is this kind of shape, and then just see that that is corresponding to this thing over here? Why can I not go backwards from this z transform to that function of time? And the basic short answer is that you could go back to that function of time as one possible candidate for one possible function that would have that z transform. Right? But there are an infinite number of functions that have that exact same z transform. Okay? If I have a z transform that is 1 at every sampling point like this, you may say that obviously f of t is the unit step. Okay? But I can construct lots of different functions that go through all those exact same points. Okay? They don't have to be discontinuous. They don't have to be discontinuous. They can be continuous. Right? And so all of those functions, every single one, if you kind of go crazy, you remember every time you draw a line, you're drawing a function, right? So any function that is 1 at all of those points will have that exact same z transform. Its z transform will be exactly 1 over 1 minus z to the minus 1. So this is the first thing that you absolutely need to understand, and it sounds maybe right now like a bit of a weird thing, right? Like, why don't we just choose the simplest one? Why don't we just choose the one that has no discontinuities? Why don't we just choose the one, like implies some kind of limit? And remember, we had this thing that what is true is that band-limited signals, if I've sampled correctly, band-limited signals, there's only one band-limited signal that goes through those points, okay? Here's the shocker though, like the bad thing. I'm going to draw a couple of signals that have infinite bandwidth. In other words, that are never band-limited. It doesn't matter how closely you sample, these signals basically are impossible to encode correctly with this idea that I could reconstruct the signal. So, is everybody up for it? Okay, I'm going to sketch a couple. Okay, there's one, the unit step. okay? Here's another one, the unit ramp, okay? Here's another one, basically any combination of the unit step and the unit ramp. None of these signals are band limited. Now you can explain this to yourself in a couple of different ways. If you're worrying like, why is this not true, okay? You can explain this to yourself in a couple of ways. I think the one that hopefully resonates the strongest, given the stuff that I've explained about the frequency domain, is that none of these things have finite Fourier series. In other words, I can express these things kind of with better and better precision as a Fourier series, but to get sharp corners, I need an infinitely large number of Fourier terms. So another way of thinking about band limiting is almost like a slope limit. In other words, or actually kind of a smoothness limit, where only functions that have this kind of smooth behavior. So like, here's what a band limited version of the step would look like. Right, so that is a step that's been taken through a brick wall filter, and all the high frequency components have been removed. Okay, because that thing can be approximated by the first couple of Fourier series terms. Right, because it's got this smooth behavior. And so this is a significant problem for us when we're trying to do the same math as we were doing in the rest of the module, because none of the building blocks that we were using in the rest of the module have the property that we would want, which is that we could safely do an inverse Laplace, and so or an inverse Z. Now, I'm saying this partly because, like, the first couple of times I taught this material, I just never mentioned any other version of inverting the Laplace transform than the one that I'm going to explain to you now, which is that the inverse Laplace transform tells you the values at the sampling points. Okay, so in other words, I can say do the Z transform on a sampled signal, and when I say do the Z transform on a sampled signal, what I want you to kind of pick from that is I'm going to take the values of the function at the sampling points, and I'm going to write them as the coefficients of this series of Z. Okay, and when you say I want to get the inverse of the Z transform, what comes out of the inverse is just a series of values for the function. Right? And obviously, if I've written it in this infinite series form, if I've written it like this, it is really as simple as looking at each of these Z's and reading off the coefficient. It's straight up, that's inverting the Laplace transform, right? Like, is going from this description to the table, to the spreadsheet. What I didn't understand is that I needed this lecture to explain to you not to do what apparently like everybody wants to do, which is, oh, I know how to invert the Laplace transform. I just go from right to left on this table. So I used to just never mention this. And what that meant is that everybody in the test, when I said like, invert the Laplace transform, or invert the Z transform, even though I had never taught you any other technique than either long division or series expansion or the other techniques that I'm going to talk about today, a huge majority of people basically felt compelled to kind of go this way and then write down a function of time. And now, weirdly, operationally, if you don't tell me that's what you're doing, you can still get full marks, as long as you use that function and then like plug in values for time and like read off the values of time, okay? But it is incorrect to say that the inverse Laplace transform of this thing is that thing, or the inverse Z transform of this thing is that thing. The inverse Z transform gives me a series of values, full stop, right? And at this point, I would like you to think of the Z transform as something that starts off by operating on sequences of values. And this whole sampling idea is just kind of a ruse to get the math to work out. Okay, so how do we obtain the inverse of this? How do we then obtain, given this, if I am here, where it is now not immediately clear what the values of the function are, right? It's definitely not as clear as it is in this expression over here. So if I have this long form polynomial in Z, super easy, right? Write it out, look at the coefficients with your eyes, write them down one by one, notice the power of Z to understand which exact sampling period that is associated with. So here the power is 0, and so the time is 0, right? Here the power is -1, so it's the first sampling time, and then if it's like a 2-second sampling time, that is time 2, okay? So as long as you keep those things straight, like reading one of these is really, really straightforward. What about when I have one of these? And I want to, it's not often that I do this, but like the Z transform section in the textbook, I'm telling you that it's built for like the 70s. It's like they don't know really computers exist at all. Or no, they know computers exist to do graphical simulation, but they don't know computers exist to do calculations. And so what they are telling you to do to invert this Z transform is to do long division, which I am telling you, you are all very thankful that you no longer have to do. This used to be the bulk of your time during a test in the Z transform, because obviously what you would have is this expression. And so let's just get that expression over here to the side. So I'm telling you I have this transfer function that looks like that, and the test question would look something like, find the inverse of. Obviously, that's not how it would be in the exam. It would be a little bit more disguised. But when you take off the glasses and the funny nose, like it'll be one of these, right? And what the textbook tells you to do is to do this. We say that that is obviously Z to the minus 2, Z to the minus 2 over 1 plus Z to the minus 1, eq. And now they're asking you to go back into the mists of time, probably during, like, I think standard 9, or I don't know what grade that is, like grade 11, right? And they're basically telling you to build one of these guys, right? So they're saying, what I'm trying to figure out is how many times does Z to the minus 2 go into 1 plus Z to the minus 1? Do you remember this? Are those supposed to be switched? Shows you how much I know. No, that's true. It's how many times does the thing go into the other thing, right? Now the process goes something like this. You look at that and you say, okay, what should I multiply that left-hand side thing by to get the thing under the surd? And you like, okay, so that's Z minus 2, and then you multiply that out. And then you subtract. And then you keep going, right? Now you have this new thing, and you ask the same question, and you develop that now by long division. I'm pretty sure it's actually the other way around. I'll edit the video to correspond.
Because it's actually carry top 1 if you multiply with Z squared, top and bottom, you get 1.
Yeah, it's Z squared divided by 1 plus whatever. Right, so the question is, how many times does Z squared go into 1 plus? That is actually the question.
But like if it's 4 divided by 2.
Long division. okay? So you can see that I don't do this, okay? Do not do this. This is how the textbook does it. This is how literally nobody else who has a computer in front of them does it, okay? How you do it when you have a computer in front of you. And we started doing this yesterday. Remember that we used SymPy. SymPy can be used to develop the Z transform in the first place, right? So you can kind of get there with SymPy. You can do this infinite sum. But you can also go backwards. And so, given a little bit of time, so we know that this unit step that we developed yesterday will have coefficients 1, 1, 1, 1, 1, right? And so how do we get there? We can just do a series expansion, right? Because that is effectively what a Taylor series is. It's the answer of, well, what does this thing look like? What does this thing look like if I approximate it as some coefficient times z to the 0 plus some coefficient times z to the minus 1 plus some coefficient times z to the minus 2 and so on. And so this, in my mind, is a significantly easier way of inverting the Z transform than doing long division. Now, if long division appeals to you, the one thing that long division has going for it, basically the only thing that long division has going for it is if you have made the conceptual decision in this subject never to turn on the computer during a test. This is how you would have to do it. I think it is the fastest way to do this if you were doing it by hand. So if you have made that decision, that is basically how you do it. Long division, not for, I will never ask you, like I will never explicitly ask you to do long division of polynomials. Because, yeah. As you have seen, I don't even really know how to do it. Yes?
So, well, how did we get the Taylor series expansion negative half?
So I have introduced a trick, okay, because this is now a very good question. The question is, the way I know how to use series is, this is a thing which is in this variable called z, and I tell it, this is the thing that I have in this variable called z, and I develop it around the point 0, and I'd like a couple of terms, and the problem is that now I get this. Okay? How do I get SymPy to give me those in terms of negative powers of z? Very easy. I just introduce this thing that I call Q, and I do a substitution. So I say, okay, let's imagine that Q is equal to z to the minus 1. And then we just do the series expansion in terms of Q instead of z. Okay, which basically goes like this. So I have use.subs Q z to the minus 1, or actually, sorry, z Q to the minus 1. And now I have all my coefficients in terms of Q. But remember, Q is z to the minus 1. And so we're getting it the right way. Relatively straightforward. Okay? So the last thing I want to go over, is that clear to everybody? In other words, when I say find the inverse of a Z transform, what I mean is not find the function on the left-hand side of the table. I want to make that very clear. I've spoken like 3 seconds about how to do it, which is like what I usually did. It's not hard to invert. The textbook makes it sound a lot harder than it is. If you have tools that do it, it's really straightforward, as long as you understand that what you're expecting to get out is just a list of values. right? Like you are 100% not expecting to find a function of time. It's super confusing, I know, because the inverse Laplace, like you did a Laplace on a function of time, and then when you did the inverse Laplace on that thing, you got back the same function of time. The Z transform just straight up doesn't work that way. Okay? So when we say invert the Laplace transform, what we mean is get back the values. That's the cliff notes. That's the whole of the deal. And you only need to know how to do that through series expansion or through the built-in routines in some of the libraries that I'm also going to show you in the notebook. But the most important thing that people think is that you can actually go back and forth between these tables without loss, which is 100% not true. And so you should interpret this table differently. You should really just think of this as the Z transform of the sampled version of that thing. And remember that little line that says you can only go one way. So I want to return to this thing that I slipped in when we were talking about shifting signals. And mostly because I know that all of you are incredibly adept by now at taking a signal like this. I know this because you all did great in the test. If I give you some random signal like this, all of you can, without any trouble, write down the ramps, the shifted ramps, or the Laplace transform of that signal, any of those different versions. You're really good at it. And hopefully it was kind of obvious to you when I did this, when I said, well, if I wanted to shift that signal up by 2, I have to multiply it by e to the minus 2 delta ts, which in our new notation, like simplified notation, is just z. But I want you to understand something special that's happened when we did that. Another way of thinking about what we did there is to imagine that we had a signal and that this z to the minus 2 was like a delay transfer function. In other words, I started out with this thing, right? And on the other side, I got this thing. And this thing was, at least conceptually, if I'm using Z transforms, a thing that looked like this, right, if that's 0. And this thing was a thing that instead looked like this. And now do you see what this is telling us? It's telling us that just like the Laplace transform, I can think of a thing in the Laplace domain as being dual purpose, right? When I show you some Z notation, up to now, I've said, oh, that's a signal. That's a thing that is sampled at certain points. That is a signal. But it's also a machine, or it could have been a machine. It's also a thing that does things to an input that it is multiplied by. And when we have it in this mode, we think about that as being the transfer function of a system, right? And the way that we kind of think about these, we can think of it just in the Z domain as I have here, like through some intuition. But we can also say, well, this is a signal, this is a machine that works in the following way. U of k, or let's say y of k, let's say this is y and this is u. How this machine works is like this. Does everybody see that that's kind of an equation that describes the behavior of the machine? This is a difference equation. In other words, it's about discrete points in time called k. And it's saying that the kth y, to get the kth y, go 2 time steps back and use that u. Right? And it turns out that I can think of doing the Z transform. If I think of doing the Z transform on a series of numbers as I have before, I can also say, well, the Z transform of y of k is y of z, and that's nicely symmetric with the Laplace transform, right? And then I can say, okay, but that means something like the Z transform of u of k minus 2 is equal to u of z times z minus 2. right? And so when I use these two definitions on my defining function for my little delay transfer function, what I end up with is something that mathematically resembles the transfer functions that we're used to working with. In other words, we're saying y of z is equal to u of z times z to the minus 2, and just as before, we can identify the coefficient of the input on the right-hand side of an equation like this. When I write output is equal to input times a coefficient, that coefficient is the transfer function. And if we're working with scalar values, you can obviously do the division definition, right? So you can say that u over y, or y over u is equal to z to the minus 2. Okay, but that's the mechanics. Now this works for difference equations of any kind. So this works even if we're doing difference equations that used to be something like derivatives. And so if you look at this difference equation over here, if I have a first order difference equation like this, where I've got the same kinds of stuff, I've got y's and u's, but now I've got a little bit of a more complicated process, right? So now there's a couple of different versions of u, and there's a couple of different versions of y at play here. But the process is exactly the same. I imagine the Z transform of the series that is shifted by a certain value simply to be multiplied by that number of Z minus 1s. Okay? And what this allows us to do is it allows us now to find the transfer function of a process. And at this point, I want you to see that we have now done the two things that we used to do with the Laplace transform, right? We used to say, okay, I can Laplace transform the input signal when I think of it as being as a function of time. I can also Laplace transform the process when I apply the rules for integration and differentiation and so on to a set of equations. The corresponding stuff in the Z transform is do the Z transform of the input signal, do the Z transform of the process that is operating on the input signal, and now I have a complete set. I know how to do the Z transforms of signals, I know how to do the Z transform of processes, and everything else works exactly the same because the transfer functions, they have exactly the same idea, that they also are in series. We just multiply them. Multiplication basically corresponds to convolution, and we can do all of those manipulations relatively straightforwardly, going from the original time equations all the way through to these Z equations. Yes?
So for the Z transform of our system equation, like if we have a block of equations, we would have to change that into a discrete difference model for any differential equations.
So there's a whole different question there. Okay, so what I've explained here is how to get the Z transform, and actually what I've explained earlier as well is how to get the Z transform of a signal that has already been sampled. Okay, and what I'm explaining here is how to get the Z transform of a system that is a discrete process. I have not said how to approximate continuous processes by discrete processes, which is a whole different lecture, which is actually literally tomorrow's lecture. Okay? But for now, you are armed with most of the tools that you need to do the tutorial, except for the very last question where I'm asking you to approximate. That will become more clear tomorrow. It is possible for you to do the whole tutorial today if you read ahead a little bit. If you'd rather wait for the last reveal tomorrow, just hang around where I introduce the idea of approximates. So up to now, just like as a line under this, everything that we've done up to now, not a single thing that I've shown you when I've talked about discrete transformation has involved any approximation at all. When I write, so when I say that, for instance, this equality over here is a true equality. In other words, if I take this signal and I sample it and it is an infinite signal and it's always 1, it is equal to that value, right? And if I have a difference equation and it starts off being a difference equation, which means it's like something that you could do in Excel, right? Like referring to previous and cells. if the process is discrete, if the logic is going step by step by step, it has an exact discrete representation. Another trap that people fall into is that they think that what I'm explaining to do is how to get from continuous systems to discrete systems. That I will only be doing tomorrow. So for now, you only know how to work with exact representations of discrete signals and processes that operate on discrete signals that can be captured in difference equation form with linear coefficients.